Hello everybody, welcome back to another video in the Probability and Statistics playlist. So what do we cover in the past videos? So in the past several videos, we've covered the following concepts. We've covered about the concept of an estimator. We've also covered unbiased versus biased estimator. And we've motivated that topic with an analogy of estimating the average height of residents in a large town. And finally, we have shown that the sample mean is an unbiased estimator. Okay, so now that we have that legwork in place, right? What is the goal for today? So the goal for today is the following. We want to show that the sample variance is an unbiased estimator. Okay, so now that we have that topic in mind, we need to establish some givens. So here are the givens. So just like we did with the sample mean, we assume that there's random variables x sub 1, x sub 2, all the way to x sub n that are independent. So remember back to the town height analogy, right? X sub 1 is a random variable, and that means that it's the event of asking a resident in town what is their height. Likewise, x sub 2 and x sub n are the events of asking resident in the town what is their height, right? So it makes sense that x sub 1, x sub 2, all the way to x sub n have to be independent random variables, because then that would mean in our town height analogy that asking a person their height, like one resident in the town, what's their height, shouldn't really affect what other residents say about their heights, right? That would be kind of weird, right? I mean, there are corner cases, but let's assume most residents are honest, right, in this analogy. So it makes sense that x sub 1, x sub 2, and x sub n have to be independent random variables. So it's like independent events, right, of, taking a data point from the population. Now, speaking of population, we're going to also assume that the population has a mean of mu and a variance of sigma squared. And given that knowledge, right, that the population has a mean mu and variance sigma squared, one question you might ask is, okay, so we know the population has a mean mu and a variance sigma squared, right? But I'm going out and asking residents what is their height, right? Well, you don't know what the resident's height is going to be unless you ask, right? But what you can say is that you might have a guess for what their height is going to be, right? And the best guess you can give is the average, right? Because that's all you know about, the resident's average height, right? An average is just a decent guess, right? So the expectation associated with x sub I is going to be assumed to be mu. And likewise, we also have this variability, right? Because not all residents in a town necessarily have to be the same height. You can have some residents who are on the shorter side, some residents who are, on the average side, and some residents who are just really tall, right? And there's going to be some sort of spread, right? Some average spread of the heights, right? So this event of asking one resident in the town what's their height, that's what x sub 1 is. And x sub 2 is going to be another event of asking another resident in town what's their height, right? So the variance or the uncertainty, right, or the average spread associated with the event of asking one resident what's their height is limited to the variance of the population, which is sigma squared, right? So the variance associated with x sub I is assumed to be sigma squared, right? And number 4, this is going to be very important. The sample variance is given by 1 over n minus 1 times the summation from I equals 1 to n of x sub I minus x bar squared. Okay, so now we have the givens established. We're going to also recall a couple properties, right? So helpful properties. So there's a couple helpful properties that we need to know. And those relate to our properties of expectation, right? So the expectation associated with, x plus y, where x and y are two random variables, is the expectation of x plus the expectation associated with y. And another helpful property is that the variance associated with a random variable is expectation of x squared minus the square of the expectation of x. So these two properties are going to come very, very well in handy in order to do our proof. So we have the legwork established right here, and we've established our problem. So in this video, we've established what are the ingredients we need to do the proof. In the next video, we're going to actually carry out the proof. So till then, tune in for the next video where we actually carry out the proof.